When you're solving a complex problem, it's not enough for your solution to just work. It has to be the best solution possible. That's the goal of optimization. Think of it like tuning a race car. You're tweaking every single component, the engine, the tires, the aerodynamics, to achieve peak performance on the track. In modern engineering, we use incredible digital tools, specifically computer simulations, to achieve this level of precision. We're going to learn how these tools let us see into the future of our designs. This standard is all about putting the power of computation to work. Our focus is using computer models to predict the impact of a design solution. Why is this important? Because real-world problems are complicated, often involving numerous factors and limitations, like cost and safety. A simulation allows us to test how a proposed solution, say a new type of wind turbine, interacts not just with the air, the mechanical system, but also with the local wildlife, the biological system, and the local power grid, the electrical system. Optimization is basically the process of making things better, cheaper, safer, or faster, ideally all at once. If your first design for a phone battery lasts 8 hours, optimization means running tests to find a way to make it last 10 hours without increasing the cost or the size. It's the final polishing stage where we use all the data we've gathered to squeeze every bit of efficiency out of our concept, ensuring our solution is truly the most effective answer to the problem. Why do engineers rely so heavily on computer simulation? Simple: time and money. Imagine testing a new skyscraper design by actually building 50 different versions in the real world. That's impossible. With a digital simulation, you can create a virtual model of that skyscraper and subject it to a virtual earthquake or hurricane, all from your computer desk. It's a safe, incredibly fast, and very cheap way to get robust data on your design's performance before any real construction begins. To optimize a design, you must understand it as part of a system. A system is just a set of parts that work together. For instance, a new self-driving car is a physical system, but it also interacts with the traffic management system, the GPS satellite system, and the human driver. If you optimize the car's speed without considering how it affects the traffic light timing and interaction between systems, you could end up creating more congestion instead of less. Optimization demands this wide-angle view. When we set up a simulation, we must clearly define the boundaries of the system we are modeling. Think of it like isolating a variable in an experiment. If we are optimizing the fuel efficiency of the rocket, the simulation focuses on the physics within the atmosphere and space. We wouldn't include the geology of Mars, because that's outside the scope of this particular problem. Clear boundaries ensure the simulation is manageable and relevant, giving us focused and trustworthy results. The language of simulation is mathematics. Before a computer can test anything, the design must be translated into formulas and equations. This could be simple algebra describing how pressure relates to flow rate, or complex physics models defining heat transfer. The mathematical model is the brain of the simulation. It's the set of rules that tells the computer how all the variables, like force, mass, and time, interact with each other in the virtual environment. The actual execution of the simulation relies on computational thinking. This involves using logic to break down complex tasks into simple steps that a computer can follow. We create algorithms, essentially recipes, that instruct the computer to take our mathematical model and run a test, collect data, change one variable slightly, and run the test again. This automated, logical approach allows us to test thousands of variations overnight, something a human could never do manually. The power of simulation really shines when you are balancing multiple criteria. A physical test can only tell you one thing at a time. A simulation can test 5 things at once. For instance, you could be designing a shipping box and simulating how well it protects the contents, how little material it uses, how easily it stacks, and how fast it can be assembled, all in the same digital run. This simultaneous testing is key to true optimization. Just like criteria, constraints are built directly into the computer model. If your design has a budget constraint of $50, the simulation is programmed to reject any virtual material that would push the cost above that limit. This automated constraint enforcement is invaluable because it guarantees that the optimized solution you finally select is not just theoretically perfect, but is also actually buildable and affordable in the real world. Simulations are fantastic for visualizing and understanding trade-offs. By varying a single design element, say the thickness of a solar panel, the simulation can immediately show you the resulting trade-off. A thicker panel is more durable, good, but more expensive, bad. You can use this data to precisely quantify the relationship between cost and durability, helping you find the sweet spot where you get the most resilience for the least amount of extra money. A single simulation run generates gigabytes of data. The challenge shifts from collecting data to analyzing it. Engineers use specialized software to process this massive output, looking for patterns, trends, and correlations. Which variable had the biggest impact on performance? Why did the material fail at that specific stress point? This analytical step turns raw numbers into actionable insights that fuel the next round of design improvements. A truly responsible engineer doesn't just optimize for the intended goal. They use simulations to anticipate unintended consequences. Your new, highly efficient water pump might be great, but does the noise it makes affect the sleep patterns of nearby residents? The simulation allows you to factor in these secondary effects, modeling noise pollution or heat output, ensuring that your optimized solution doesn't create new, hidden problems for other systems. Complex problems often involve system-to-system interactions. Consider designing a high-speed train route. The physical structure of the train, one system, interacts with the local geology and seismic stability, another system, which then interacts with the safety regulations, a third, social system. Simulations can be complex enough to tie these different domains together, allowing you to see the holistic effect of your design across various disciplines. Computer simulation turbocharges the iterative design cycle. When you test a physical prototype, it takes time and money to rebuild it. In a simulation, you can run hundreds of virtual tests, analyze the results, tweak the mathematical model, and immediately run another 100 tests, all in a fraction of the time. This high-speed iteration is how engineers achieve rapid optimization, speeding up the design process exponentially. One of the most powerful optimization tools is parameter sweeping. Imagine you have 10 different choices for 10 different parts of your design. Parameter sweeping is a simulation technique that tests every single possible combination of those choices. It's like checking every possible setting on a dial until the maximum performance light turns on. It mathematically guarantees that you find the single best combination of all factors, leading to the truly optimal design. The results from a simulation are only useful if you can trust them. This brings up validation and verification. Verification means checking the code and math of your model to ensure there are no errors. Validation is harder. It means comparing the simulation's output to actual, real-world data from a small physical prototype. If the simulated prediction matches the real-world observation, you've validated your model and can trust its optimization results. Modern engineering optimization must include environmental impact. Simulations can track specific metrics like the energy required to manufacture a component or the amount of waste generated at the end of the product's life. By building these factors into the criteria, engineers can optimize for sustainability. They can compare solutions and choose the one that not only performs best, but also has the lowest carbon footprint over its entire lifespan. A final, crucial step is communicating your computational results. You might have the perfect, optimized design, but if you can't clearly explain the data to the people who will fund or use it, your work won't go anywhere. Engineers use clear visual aids like charts and graphs to show why the chosen solution is superior, detailing the trade-offs managed and the evidence from the simulation that backs up their final decision. In the 21st century, the greatest global challenges, from fighting disease to building smarter cities, require us to optimize solutions efficiently and responsibly. The skill you've learned here, using computational simulation to model complex systems, it's foundational to that effort. It empowers you to design not just with intuition, but with precision and foresight, ensuring that your contributions as a future engineer will be both powerful and positive for our world.